Okay, this is my first magnetic forces reassessment, and as you can see here, there's a bar here that's made out of a new conducting material. It's 9 centimeters long with a rectangular cross section that's 4 centimeters wide and 2 centimeters deep. The bar is inserted into a circuit with a 1.5 volt battery, which is here, and carries a constant current of 0.7 amps, shown here. The resistance of the copper connecting wires in the ammeter and the internal resistance of the battery are all negligible compared to the resistance of the bar. Using large coils not shown in the diagrams, a uniform magnetic field of 1.7 Tesla is applied perpendicular to the bar, which is to the left, shown here. A voltmeter is connected across the bar with the connections across the bar carefully placed directly across from each other as shown, which is here. And you can see they're placed across from each other. The voltmeter reads negative 0.29 millivolts. There is only one kind of mobile charge in the bar material. So the first question I'm going to answer is, what is the sign of the mobile charges in the bar and which way do they move? So on the back here I've drawn two different scenarios because it's kind of a trial and error thing to figure this out. In the first scenario, I have positive mobile charges, which are going to be moving in the same direction as the parallel electric field, which is down in this case. And by doing V cross B, we're going to get a magnetic force which is into the page by using the right-hand rule. And so by doing that, we can see that there's going to be... So we can see here that there's going to be a negative charge buildup here on the front of the plate and a positive charge buildup over here on the back of the plate. And so the E perpendicular is going to move from the positive to the negative. And so in this case, that's not what we see, because then we would see a positive reading on the voltmeter and we actually see a negative reading. So we have to know then that we have negative mobile charges, and in that case they move opposite of the parallel electric field. So they're going to be moving up, and doing V cross B, we still get a magnetic force into the page, but in this case we're going to get a positive charge built up on the front of the plate over here, and on the back of the plate we're going to get a negative charge built up. So E perpendicular is going to move in the direction going from positive to negative, instead of, in this case, from positive to negative this way. So it's pointing towards the negative in this case. So then we will see a negative reading. So we can conclude that the mobile charges are negative. The second question, how long does it take for the mobile charges to go from one end of the bar to the other? So we just use this equation that we know, and we know that E perpendicular is equal to the change in potential over D. So we rearrange that and plug in this. And so we know the change in V because they gave us that on the voltmeter reading. We know B, that was given to us, and we know D. So we just plug all that in. And then, now that we know the velocity, or I'm sorry, not the velocity, the drift speed, we can do change in T, which is going to be the 0.09 meters that they gave us divided by the drift speed, and that'll give us the seconds. So the third question I'm going to answer is, what is the mobility U of the mobile charges? So we know that the mobility times E parallel equals the drift speed. So by taking E parallel, we know that it's the 1.5 volts of the battery divided by the 0.09 meters that it travels across, and that gives us E parallel. And then we can take this equation and rearrange it for this, and just plug in the 8.5 times 10 to the negative 3 that we found up here for the drift speed, divided by E parallel that we just found, and that gives us the mobility.